In this lecture, I'm going to talk about how we add branches and jumps to the CPU design and what the implications of that are. We decided to just skip the load and store instructions for now, since we're running a little bit behind schedule. And frankly, there's nothing too interesting to do with those, right? So since we're limited to on-chip memory. So we've got 6 instructions that we want to add, 3 of which are branches. That mean they're conditional change of control instructions. They check for some condition, and if the condition is true, then they go to a program counter that isn't necessarily the next program counter value. And the jumps are unconditional. The other difference is that the branches are I-type instructions, and they use PC relative addressing. So if your offset is 0, that means just go to the same place whether you take the branch or not. If the offset is 1, you would skip the next instruction that appears after the branch. And if the offset is -1, then you'd be branching to yourself if the branch is taken, right? Branch instructions, because they're I-type and there's a 16-bit immediate field, they give the ability to skip up to 32,767 instructions forward or negative 32,768 instructions backwards. If you need to jump more than that, then you have to use a jump. And if you want it to be conditional, you'd have to use a jump in conjunction with a branch. Jump and link are J-type instructions, which have a 26-bit pseudo-direct address, which in our case it's a direct address because our PC address is only 12 bits. So you can actually fit the whole address in a jump in our case. And then the jump register is an R-type instruction. You guys remember that stuff from 212? Okay. Okay, so I talked about this. In assembly code, you would use a label, but when you assemble this, the label is just transformed into an offset, a number of instructions to skip, either forward or back, if the branch is taken. The target address, as I mentioned, it's signed value, so you want to sign extend that. And the program counter that we want to go to next would be whatever program counter is in the fetch stage plus the sign extended immediate of the instruction in EX, the EX stage. And the earliest we can resolve a branch is in the EX stage because we don't know whether we're going to take the branch. We can't determine whether we're going to take the branch until we've fetched it and we have the instruction in the execute stage. You guys with me? So this creates a problem. The problem is that you don't know if you're going to branch until after you've executed the branch instruction. But by that time, it's too late. You've already fetched the next instruction that appears after the branch in the code, right? Which is usually called the fall through instruction, right? So you have this control hazard. You guys remember that? You should have covered that in 212, but that's something that's usually right at the end of the semester, and some of the instructors don't get to it. So here's an example. You got a branch here, so you've got an add that's fetched in cycle 0, a second add that's fetched in cycle 1, and then you've got your branch that's fetched in cycle 2. Now, if the branch is not taken, it's not an issue because the instruction after the branch which is the fall through, it's whatever instruction appears right after the branch in the code, that's being fetched while the branch is being executed. So if the branch is not taken, you don't have to do anything. You just keep going. You just execute. You send the instruction that was in the fall through slot. It's already been fetched, so just execute it. But if you take the branch, and that's what this T stands for here. If you take the branch, then we have to change the program counter. we have to update the program counter while the branch instruction is in the execute stage. You guys with me? So you update it, and then you're not going to be able to fetch the instruction at that address until the following cycle. So what ends up happening is that the instruction that was fetched after the branch it has to be converted into a stall. It has to be ignored. Right? So basically, you fetch it, and you allow the instruction, the instruction to fall through, which we don't intend to execute because we're branched. You allow it to just run its course through the pipeline. You just make sure that it doesn't get to change anything. It doesn't get to affect anything. You guys with me? So what that means is that the branch was fetched in cycle 2, but the target of the branch is not fetched until cycle 4. Right? Because the instruction that was fetched in cycle 3 is being thrown away. So you've essentially inserted a stall into the pipeline. You've wasted a cycle. Likewise, in cycle 5, when that fall-through instruction would have been finishing, nothing effectively gets finished. It's a wasted. It's a stall. It's a no-op, basically. So there is an instruction that rolls off the assembly line after cycle 5, but it doesn't do anything. It's a waste. So what that means is that every time you take a branch, you waste a cycle. You lose a cycle. You have a whole cycle where the CPU is not completing an instruction. So the more branches you have, the more performance you lose, and that's an unavoidable fact in any CPU. Luckily, because we only have a 3-stage pipeline, we only suffer 1 cycle of penalty for a taken branch. But if you have a CPU that has a deep pipeline, like a Intel or even an ARM processor, you're going to lose multiple cycles. You're going to have to convert multiple instructions that are at various points in the pipeline. They'll have to be converted to stalls. So branches are devastating to performance. Okay, any questions about that? Okay. So how do we add support for branches and jumps? We just go to the fetch stage and allow the program counter to accept a value other than PC+1. So we want to be able to feed in, we want to be able to override the natural incrementing of the program counter. So we want to be able to put in branch address, which is the calculated branch address, PC plus offset. The JType address, which is the pseudo-direct address, right? This is in the JType instruction, or a register address if you're doing a jump register, right? Where you do a jump register, you grab a value from the register file and you shove that into the PC. So there's 3 alternative sources for the new program counter that we have to be able to add support for. Which, how do you do that? You just add a mux. You just the same way that we did, like, for example, for the ALU, when we add support for I-type instructions, you have to add a mux to the second ALU input to allow you to support the immediate as the second operand, right? Any questions? So I think that's the easy part. The harder part is the stall. So if a branch is taken or if you execute a jump, you select one of these other 3 guys for the program counter, but it's going to cost you a cycle to get the instruction at that address. So in the meantime, you have to ignore whatever the current instruction being fetched is. Right? So you need to have a stall signal as well. So the control unit or whatever determines whether there's a taken branch, it has to assert a stall signal, which is then delayed for 1 cycle, and in the next cycle, that stall signal tells the control unit not to do anything for that cycle. For every cycle, stall is asserted. You guys with me? And one other thing, there's this instruction jump and link. You guys familiar with that? Have you heard of jump and link?
Heard of it, don't remember what it does. It's like a call, right?
Yeah, it's a call. Yeah, if it were an Intel processor, it would literally just be a call instruction. Some ISAs call it call. It's a jump, but it provides a mechanism to return to where you would have gone had you not jumped. So that's the link address. And it's used to implement, in my day they called them subroutines. Now they're just methods, I guess, function calls, method calls, right? Where you would, you want to jump somewhere, but then you want to return from where you came from. So to implement that, MIPS will, in the hardware, take the program counter and put it into register 31. That's your return address. So subroutines are basically jump and link somewhere, and then when you're done with the subroutine, you do a jump register to register 31 to return. That does complicate things, though, because we have to add a data path to get the program counter into the register file. Which, but once again, it's just, the idea there is just adding more inputs to the MUX that we already have. We already have a MUX that allows us to select different inputs to write to the register file, so we're just going to add to those MUXs. Any questions? Okay. Okay, so let's look at some diagrams. So this is essentially what we want to do. We have the fetch stage, and previously we had the program counter feeding the address of the instruction memory, and we had the program counter being incremented by 1 and then fed back into the program counter. So it was just a counter. But now we want to add this MUX that allows us to select whether we want to put PC plus 1 in or some target that comes from the execute stage. Make sense? So we're just putting a MUX there, and we're going to add a control signal called PC source that will select where the PC sources its next address from. And then the stall I mentioned was, conceptually what the stall is it's like having a stall signal that takes the instruction that would normally come out of the instruction memory and converts it to a no-op. Does that make sense? And then to add a little bit more detail, we've actually got 3 possible branch targets depending on which of the instructions we're executing. So the branch address, the JType address, and the reg address. These names are mine. I came up with these myself. The idea is that there's 3 different ways you can calculate where you want to go. If it's a branch instruction, it's PC plus offset, right? So that's the branch address. If it's a jump instruction, a JType jump instruction, you just pull the address directly out of the instruction itself. And then if it's a jump register, you have to get the address from the read data 1 coming out of the register file. So the idea is that these 3 values are going to be set for every instruction, even if it's not a branch. Well, you might say, wait a second, if it's not a branch, that's just garbage. Yeah, but it's going to be garbage. It's garbage in the sense that you're interpreting data in the instruction as an offset, which is not supposed to be an offset because it's not a branch or not a jump, for instance. But that's fine because these guys will be don't cares if the PC source is not selecting that value. You guys with me? So you calculate all 3 of these guys concurrently, and then you may or may not use them depending on whether you're doing a jump or a branch. Does that make sense? And by the way, each one of these, this is just essentially one assignment statement in Verilog. You're just going to say assign branch address equals PC fetch plus instruction EX 11 down to 0. That's it. That's just one line of code that will generate that guy, and then it will become available always. And then whenever we want, we can use the PC source to enact one of those 3 target addresses. Okay. Okay, so this is a little bit, I'm trying to, this diagram is a little, provides a little bit more details. So you've got the underscore EX here signifies that these signals are being generated as a function of the instruction that's in the execute stage, right? The program counter has the underscore fetch after it because it applies to the instruction that's being fetched. You guys with me? Now the stall is the one that's a little confusing, I think. So if I execute a branch that's taken or a jump, I have this stall that comes out of the control unit. That stall is supposed to be applied to the instruction that's in fetch, that's being fetched. You guys with me? So even though it's being generated out of the execute stage, you want to apply it to the instruction being fetched. So you generate the stall fetch, and then I think the easiest way to implement this is to just delay that. This is a register. You delay that one cycle, and then it becomes stall EX. So stall EX is stall underscore fetch from the last cycle. And so if you stalled the instruction that's in fetch, then the next cycle that instruction will be in execute, and you'll have a stall execute that corresponds to that. You guys with me?
So you mentioned that that's a register. So those are supposed to indicate when you're holding it for a cycle?
Right. Yeah, so the instruction the instruction that comes out of the instruction memory is in the execute stage, because it takes that instruction EX isn't the real instruction until the following cycle. Why? Because the instruction memory has a 1 cycle delay to read, right? So PC fetch will be 12, for instance, and then in the next cycle, the address of 12, the instruction at address 12, will then be on instruction EX, right? But if I had stalled that instruction, then stall fetch would have been asserted back when the PC fetch was 12 and the instruction EX didn't even exist yet, or it was the previous instruction. And then in the next cycle, I'll have not only the instruction, but I'll have the stall from the last cycle. You guys with me? And then the stall EX would just signifies whether I'm stalling, meaning don't do anything. It goes right to the control unit. Make sense? Now notice what's happening though. You've got a loop here, and this is a very common bug that comes up. If the control unit generates a stall and then it acts on that stall, you got to make sure that you've got a cycle in there, right? You've got a circular dependency. So it's really important to have this delay, because if you don't put it in, it'll go into you'll have an infinite loop, but it's not an infinite loop like a program infinite loop. It's a combinatorial loop, right? Meaning that you basically end up making a quasi-sequential logic circuit here, right? If you do this and then you simulate it, model sim will just hang, right? And those are hard to track down. So make sure that because you have a loop here where this guy is not going to generate a stall if he's being stalled, right? Make sense? So you gotta break that loop up with a register. Okay, inside the execute stage, you've got PC fetch coming out of the fetch stage into the execute. Why do we care? Well, there's two reasons we need that. One is the program counter is used to calculate the branch target, right? Make sense, right? The program counter plus the offset is with the branch target address. And also, if we do a jump in link, we're going to end up having to store that program counter back in the register file, but that doesn't actually happen until write back. So that PC fetch is going to end up having to be delayed again for the write back if we write that back. Make sense? Okay. Oh, and let's see. Yeah, so PC fetch plus the, that's wrong. That was back when we had a 10-bit PC. This semester we increased this program counter to 12 bits, so this should be 11 down to 0. There we go, sorry. So the branch address EX is 11 down to 0, and we're going to set it to PC fetch, which is already 12 bits, plus the instruction 11 down to 0, the rightmost 12 bits of the instruction. The J-type address is just instruction 11 down to 0, because the jump instruction can contain all 12 bits of the instruction, and it's not relative to the program counter. And then if you do an R-type jump register, the address you jump to comes from the RS register, and that corresponds to read address 1, 11 down to 0.
Do you want to update the ones on the left?
Oh, yep. Good call. 11. Yeah, we try to change things from semester to semester. This is one of those things I forgot to update. Having a 12-bit PC gives you 4 times the program size, maximum program size, as having a 10-bit PC. You can blame Charles for that.
Always blame.
Okay. Okay, and then this slide is only showing, it's showing 2 things. One is, how do you resolve a branch? Well, it depends what branch instructions you have, which we'll go back to that in a minute. The other thing it's showing is, if you do a jump and link, you have to add a hard-coded 31 as an option for the write address, and you have to add a delayed form of PC fetch as a possibility for the write data, which that ends up feeding into that MUX. So remember the MUX, now you've got a 1, 2, 3, 4, 5 input MUX here for writing data back to the register file. Right? You've got R, which is for a lot of the number crunching stuff, high and low for move from high, move from low, the GPIO in if you want to read the GPIO, and now we've also got the program counter, the delayed program counter fetch, which I call the program counter EX, which is an option for doing the write back. You guys with me? Okay. Okay, now let's go back and talk about branch resolution. So which branches do we have? We have branch if equal, branch if not equal, and branch if greater than or equal to 0. How do you resolve those? How do you know if you're going to take those branches? Anyone know? So equal 0 and not equal 0 is the reason why we have the 0 flag coming out of the ALU. You guys remember the 0 flag? So you take the 2 inputs, you subtract them, and then if the result is 0, the 0 flag will indicate that they were equal, right? Or not equal if you complement that, right? Branch if greater than or equal to 0. I used to do this back in the old days. I used to do this thing where I would take so branch if greater than or equal to 0 takes just 1 register. You guys remember this? So if you do branch if equals 0, Q, it takes 2 registers. So you're comparing 2 registers. But branch if greater than or equal to 0 just takes 1 register. So you're taking that 1 register, you're comparing it to 0. So I used to take that register, that's in the RS field. So I would take that register, I'd stick it in the ALU, and then I would use the MUX, the ALU MUX, to put in a hard-coded 0. And then I would do a set less than operation on the ALU, and if the result was 0, then I knew A was not less than B, meaning that A must be greater than or equal to B, right? And I did that for a long time. Like, I did it that way for, well, when I say I did it that way, I suggested that the students in this class do it that way. I advocated for that approach. But it was actually kind of dumb, because all you really have to do is look at the sign bit for register, whatever comes out for register 2, read data 1. if the sign bit is 0, then that means that in 2's complement, a 0 sign bit means greater than or equal to 0. So why waste why modify the mux or the ALU mux and do an SLT operation? It's not necessary. All you got to do is look at that one bit, the sign bit. Make sense? So basically, depending on whether you're comparing 2 registers or 1, the branch resolution is either do a subtract on the ALU and look at the 0 flag coming out, or look at the sign bit of the read data 1 register. Okay, so that's pretty simple, I think. If you had a branch if greater than 0 instruction, that would be a little bit more complicated. Because greater than 0 is harder to test, because the sign bit won't tell you if it's greater, it just tells you if it's greater than or equal.
Like sign bit and not equal to 0.
Yeah, that's right. You could do it that way, a combination of the two, yeah. Of course, even if you did that, though, you'd still have to force a 0 into the ALU.
Why do you need to use the ALU output?
Well, you could look at like all the bits. You could do a reduction operation, like you could do a NOR of all the bits. So if they're all 0, you get a true. That would work too. But that's the reason I didn't include that in here. Actually, I don't even know. That might even be a pseudo instruction anyway. I don't know if there is a branch if greater than 0 instruction. It may not even exist.
There is.
Sometimes there is. Sometimes there are just a pseudo instruction. Okay. So I think that's about it. So we've got a test program. Okay, and then, so the lab 5 will be our final lab. We had to take one of the labs off because we extended lab 3, the RPN calculator, right? Or was that, yeah. So lab 5 is the lab that you are allowed to drop if it improves your grade. Of course, if you do that, you can't drop one of the exams. Okay. We will probably have to assign lab 5 electronically because Charles, so we have an exam. Our exam is, oh, actually we're gonna have lab though next week, right? Yeah. So we'll assign this, yeah, we'll officially assign lab 5 in lab next week after the exam. But just to give you a little preview, the idea is that we want to write a program where the user puts a value in on the switches, just like we're doing for lab 4, right? So the switches are 18 switches, so that gives you the ability to put in 0 to 256K, right? Which is 2 to the 18th power, right? An integer. So we'll just say it's an integer, just like it is now. Then we want to calculate the square root and put the result on the hex displays. So you'll be reusing, the hex decoders again and the base 10 conversion code again. Right? We want to show the square root in base 10. Now, what's the problem with that? Well, the problem is that most numbers don't have an integer square root. Most integers, when you take the square root, they give you a fractional value, right? So how do we put a fractional value on the 8 7-segment decoder, or 7-segment displays, the 8 base 10 digits? Well, we're going to have to use, we're going to have to assume that there's a decimal point in there. So we're going to have 3 digits. The first 3 digits will be whole numbers, and then the last 5 digits will be the fractional numbers, but in base 10. Make sense? You might say, well, how'd you pick 3? Well, because if you put the maximum number on, if you put all the switches up, it's 262,000. If you take the square root of that, it's 511 point something. So it's impossible to have any more than 3 digits, right? Non-fractional digits when you do the square root, right? Also, if you look at well, I'll get into that in a minute. Let me back up here. So how do we do the square root? There's a lot of ways to calculate square root. The easiest way is in the slowest way, but I think is the easiest way conceptually, is to just do a binary search for it, where you basically you make a guess, and then you test your guess, right? So you make a guess, and then whatever your guess is, you square it, and then you subtract the number you're taking the square root of, right? You guys with me on this, right? So if your guess is x, if you're finding the square root of value s, that's the input value from the switches, s, right? You make a guess, you call that x, and then you square x and you subtract s. So you say x squared minus s. If you've guessed correctly, the difference will be 0, right? If x is the square root of s, then that means x squared minus s equals 0, right? If you guess too high, then this will be a positive number, and if you guess too low, this will be a negative number. So if you guess incorrectly, you know where you are relative to the right answer. You know if you're too high or too low, right? So if you're too low, you increase your guess, and if you're too high, you decrease your guess, right? But by how much? Well, that's the question, right? I mean, you have to have an idea of, in order to do that, you have to know, in order to know how much to increase your guess, you have to know what sort of ranges you're talking about. Well, we know the range because the biggest number we could put on there is 256K, right? So you start the adjustment that you make can just be half of the range of answers, right? So the answer that you're giving the user is going to essentially be 0 to 512. Right? So if you're wrong, if you're too low, you add half of 512, 256. But if you're wrong again after that, you have the difference. So if you say, I'm too low, if you start, let's say you start at 0, right? If you're at 0, you're probably going to be too low, right? So probably what's going to happen is you're going to say 0 squared minus s, going to be a negative number. So you say I'm too low, so you're going to add 256. You're going to square 256. You're probably going to be too high, and then you're going to, if you are, you subtract 128. And then if you're too low, then you add 64, and if you're too high, you subtract 32. And that way you can zero in on the answer that way. Yes?
Could you kind of like rerun through that example with like your number being like 100 and square root being 10?
Yeah. Well, here's an example here I've come up with. So let's say your value is I'm sorry. I'm sorry. Let's say what is it? This is for, yes, 2. Sorry, yeah, 2. Square root of 2. So my x will be 0. I'll start out with 0. So 0 squared minus 2 is negative 2. So I get negative 2 means I'm too low, right? So I'm going to set my step amount, which is like another variable. Right? You initialize this step. It's like it's like a register. It's in a register. Make it 2, and then because this is just for the sake of this example. This implies that the answer has to be in the range of this plus twice that, right? So the answer can only be, in this case, if I start my step at 2, then my upper bound for the answer is 4, right? So you're going to set your step to be half of the range, essentially, for the answer, right? So in other words, if I were to use this same algorithm and I put 16 in here, then I could get close to the answer, but if I put something bigger, like 25, then this thing wouldn't work because the step wouldn't have been high enough for that, right? I wouldn't have been able to reach the answer, right? Is that right? 5, yeah. Make sense? So I'll start out with 2, and then I'll make my guess 2, but now 2 times 2 is 4 minus 2 is 2. That means I'm too high. I got to come back down. So my step is 1, so I'll bring 2 down to 1. 1 squared minus 2 is too low, so I got to go upwards again. So my step is 0.5. I bring it up to 1.5. 1.5 squared minus 2 is, I guess 1.5 squared is 2.25, right? So 2.25 is my new value. It means I'm too high. So I bring it back down to 1.25, which is too low. So I bring that up to 1.375, which is obviously too low. So I bring it up again to 1.43, which is too high. Then I bring that down to 1.40. And eventually it will converge on the answer, right? So every time I guess, I have the adjustment step. And that way I zero in on the answer. Yes?
Don't you need to have like some epsilon you can be within? Because otherwise you just keep going forever.
Yeah, so in this case, it's going to be our machine precision. So, I mentioned the switches allow a value between 2 to the 18th minus 1, which is 262,143. This number, if this were 262,144, then it would be an even square root of 512. 512 squared is 262,144. This is just under that. So the square root of this number is like 511.99999, something like that, right? Makes sense? So I have a range for both the inputs and the answer here, right, based on the switches, how many switches I have. Also, the BCD display is 8 digits. And so I'm going to assume that 3 of those digits are non-fractional and 5 are fractional, right? So I'm going to use an 8-5 fixed point for the displays in base 10. Make sense? So you see where I'm going with this. I ultimately, what I need to know is how many of the bits are going to be fractional, right? I know how many of the base 10 numbers are fractional, 5. But how many of my bits are going to be fractional? Okay, well this will give me a precision of 1 over 10 to the 5th power, which is 100,000. So this will get me within 100,000th of the answer. That's the limitation of my displays, my hex displays, right? That's the most accurate I can get is the nearest 100,000th on my hex displays, right? Why? Because there's 5 fractional digits. It turns out that that is roughly equivalent to 2 to the negative 14th power, which is 1 over 16K. That's not right. Well, yeah, actually it is. Yeah, it gets me a little higher though. This is actually 6.1 times 10 to the negative 5th power. So, and this also makes sense because if I have 14 fractional bits, how many non-fractional bits does that leave me? 32 minus 14, 18, right? And that's how many switches I have, right? So it works out because I got 18 switches, and I'll put that in my register as the integral bits, right? That leaves me 14 fractional bits. Make sense? Now there's a way we could get close. Now I mean the problem is that this is actually less accurate than the hex displays, because the hex displays are 10 to the negative 5th is the unit in the last place, whereas a 14 fractional bit is 2 to the minus 14th unit in the last place, which is actually 6 100,000ths, right? So what that means is that your accuracy will actually be within 6 digits of the rightmost hex display, right? So you're probably not going to be right on, but we only require this level of accuracy.
You mean like a factor of 6, not 6 digits?
It'll differ in as much as 6 of the rightmost digits, right? So, in other words, your rightmost hex digit might be slightly off. There'll be some approximation error there. So what that means is that when you get the number from the switches, using your GPIO instruction, shift it 14 bits to the left. Right? Now keep in mind, though, that when you do that, your sign bit might change. Right? When is your sign bit going to change? If you put the first switch up and then you shift it, it's going to be a negative number. Right? Because remember, right, if you shift it by 14 bits, you're using the sign bit. So anything you do with that should be an unsigned. When I say everything, I mean the multiplies that you do should be an unsigned multiply. Okay? All right. And then you might say, wait a second, hold on. What happens, like, how do you do the base 10? Well, the base 10 thing is easy because when you're done, you'll end up with an answer that is in binary fixed point, right? But you want to convert it to decimal fixed point. So all you got to do is, when you're done, multiply the result by 100,000 and then convert it to base 10. You guys with me? Now the only problem is these hex displays actually have a decimal point, but they didn't wire it up. They didn't draw the wire from the FPGA to the pin that will light up the decimal point, so you have to pretend you have it on. Right? Yeah. Actually, they have, if you look at here, if you look at these boards, it's kind of interesting. They've got, you know, we've got 8 green LEDs, which you guys know, you use them, right? But it turns out there's actually 9 green LEDs, because one of the green LEDs is actually between the first 4 digits and the last 4 digits. So I think that LED was supposed to be maybe a decimal point, except that restricts you to having 4 integral bits and 4 fractional, or 4 integral digits and 4 fractional digits, which we want 3 and 5, so it doesn't work for us. Okay, anyway. In the answer to your question, how do you know when to stop? Your step is going to, what do I say the step's going to be? Half of 512, right? 256, right? 256 in fixed point, meaning you take 256, which is bit 8. You guys following this? It's bit 8, because 2 to the 8th power is 256. And you have to convert that to the fixed point, meaning you have to shift it 14 bits to the left, which means now it's bit 8 plus 14, which is 22, right? So your step is just going to be bit 22, like a 32-bit number with bit 22 turned on. Make sense? Why? Because it's 256 in 14-bit fixed point, right? And then every time through this algorithm, you divide this step by 2, you shift it by 1, right? So what does that mean? This algorithm will iterate for 22 iterations. Always 22 iterations. Well, not always, because I take that back. Because what happens if you take x squared, subtract s, and you get 0? Well, you have to stop, because if you don't stop, you're going to pass up your correct answer, right? Like if you actually get the exact square root, you want to stop this algorithm, because otherwise you'll keep, you'll overshoot it, right? So if you get the right square root, you got to bail. But if you don't get the right square root, if you have some number that requires you to go through the whole 22 iterations, and you go through the whole 22 iterations, and you're done when the step becomes 0, because you've shifted all the bits off, or you shifted the 1 bit off. You guys with me? Okay. All right. So there'll be more details in the lab sheet for this, but that's the idea. Oh, and I had some slides about fixed point. Okay, so let's talk about the design now. Let's go back. I did a demo last lecture. I thought that worked out pretty well, so I thought we'd do that again. Let's see. Uh-oh, that's the wrong one. Sorry. Lecture stuff. Here we go. All right, so this is the... hold on a minute. There we go. Okay, this is the CPU that I showed you guys last time. I added some comments, and I added the GPIO in and GPIO out to the module line here. Right? But otherwise, it's the same. The only other thing I changed was, and this version's on Dropbox, by the way, I updated it. The only other thing I changed in here was in the control unit, which was down at the bottom, I added default signals here. So I didn't have those in the version I did in class. And I told you back when I first talked about always calm that you want to have default signals here because you don't want this to turn into a latch, right? So by default, I'm going to set my ALU opcode to add. Because why? Because I think in most cases you're adding with ALU. For most instructions, you want to just add. The reg write is defaulting to 0 just for safety purposes, even though most instructions do write to the register file, but you have to be careful with that. You don't want to unintentionally write a register. So I'll set that one to 0 by default. And the shift amount is going to be instruction EX 10 down to 6 by default, which is just taking the shamped field from the instruction and sending that into ALU. Make sense? Okay. And then the only if condition I have here is if the function code is 100000, which is the add. So I've got add. I think that's add, right? Make sure. Add, yes. Okay, so what do we want to add to this? Let's see. Let's come up with a program. Let's first of all let's add a few I-type instructions. How about that? In fact, let's come up with a list of instructions we want to add. So we've got add. We want to add IU because this instruction is what is the translation for the load immediate instruction, which is a very common instruction. A load immediate is a pseudo instruction that gets translated to add IU. So this is the way you initialize registers. You guys with me? What else? LUI is important, load upper immediate. We need that to load in large numbers into the register. ORI, that's how, if you have a big number you want to load in, you do a add IU, you do a LUI followed by an add IU, and then you OR them together. Or no, I'm sorry, take that back. You do an LUI and then an ORI, right? If you're putting a big number into a register, otherwise you just use add IU. And then branch not equal. Make sense? It's cool. So we'll see if we can get these done today. Okay, so add IU, start with that one. Add IU, UI. UI? Add IU, there it is. Okay, this one has an opcode of 001001. And actually, these guys are the same. Add I and add IU, they do the same thing, so we might as well just implement them the same way. So if we go to, let's see, can I? Yeah, there we go. Okay. Okay. Can you guys see that okay? Okay. Okay. So I'm going to add a condition here that I should have put in last time, but we should really check to see if instruction 31 down to 26, which is the opcode, that's supposed to equal 0. You guys with me? So for the add instruction, we need the opcode to be 0 and the function code to be 100000. All right, let's let's add our next instruction here. Else if instruction ex. Oh, this also needs to be instruction underscore ex. Sorry, my fault. Okay, if instruction underscore ex 31 down to 26 equals 6 apostrophe b, and then I'm going to just copy this directly from here. Paste. Or instruction ex 31 down to 26 equals 6 apostrophe b, this guy. Okay, now if I'm doing an add or an add u, the opcode is going to be add, so I can leave that alone. I've already got a default for that. Reg write, well, the reg write needs to be overridden because I do want to write a register. So reg write underscore ex equals 1b1. Oh, the other thing I changed, I'm sorry, I forgot. One thing I forgot to mention here. I separated some of these always underscore flip-flops out too to make this a little bit more clear. I've got the fetch stage and I separated that from the pipeline registers. Right? Now one of the things I just realized, when I did that, I left in, you see reg write here? Right? I assign reg write there and I also assign it down here. Right? So that shouldn't be there. That's redundant, and it's double driving reg write. So I'm going to take that out. Write address, same thing, and low write back, same thing. Right. So now I just have the fetch stage is the thing that clears the PC fetch and the instruction ex on a reset, and this is the line of code that grabs a new instruction from memory and increments the program counter. And then down in the pipeline registers, I clear reg write on a reset, and then I always transfer reg write ex to reg write back on the clock edge. And then the write address I transfer in from the RD field, and the low is transferred from low ex to low write back. So you're delaying all those by one cycle. Everyone see that? Okay, so I want to write what else do I want to do here? What do I still have to do? Well, I have to get the immediate into the ALU. Can I do that? No, I can't right now because the ALU it's got A and B, EX, which are the same values that are coming out of the register file. Let's see that? So the register file has read data 1, read data 2. Those are connected to signals called AEX and BEX, which are then just connected, hard-coded directly to the ALU inputs. So I need to put a mux. I have to mux this input on the ALU. So I have to basically break that connection and replace it with another something else. I'm going to call it. Actually, no. Let's take that back. I'm going to leave that. I'm going to break it over here. I'm going to call this one read data 2. So I've renamed the signal coming out of read data 2. I've called it read data 2 EX. So I've broken that connection by making it so they know the output from read data 2 and the input to B no longer have the same name. So that I've sliced that wire. So now I have to declare read data 2 EX. So I'm going to put it here under ALU signals. And I don't know. I'll create another little section here with a comment. I'll call it reg file signals, and I'll say logic 31 down to 0 read data 2 underscore ex, and now I have to have something that sets that. So I'll put that here, ALU mux. I'll say b underscore ex, actually I'll say assign b underscore ex equals, let's see, what do I want to look at? The condition is ALU source ex. If that equals 0, should I make it 1 bit? I'm going to have to make it 2 bits eventually because I got to support 0 and sign extending, so I'll just do 2 bits. Then I'll make it read data 2 underscore ex. Otherwise, it'll be what? It'll be instruction underscore ex 15 down to 0. Do I want to sign extend or 0 extend? Well, I guess I got to do both. Yeah, I'll do both. So I'll say if ALU source ex equals 2b1. This is 0, by the way. I don't know how that got deleted. Then I'll say this will be sign extend, so I'll do um, 16 instruction ex bit 15. I'm going to replicate that 16 times, and then I'm going to concatenate that with the lower 16 bits. Wait a minute.
I think you have to surround the 16 concat ones with extra brackets.
Oh, right. Yep, you're right.
Bracket there.
Yep, you're right. Yeah, that's a weird, I never can get used to that syntax. So to replicate, you have to put brackets around instruction ex15, then brackets around the 16 part. Right? Okay, there we go. Okay, else it's going to be 16 b0 comma instruction 15 down to 0. Instruction ex. I always forget the ex there. All right. Okay, everyone see that? So that's a ternary statement, and it's a nested ternary statement. Three options. I only have to list the first two because the third one is a default. So if the ALU source is 0, then it's just the way it worked before. But if it's 1, I'll bypass it and send in the sign extended immediate. And if it's either 2 or 3, I'll send in the 0 extended immediate. So now I have to declare ALU source EX somewhere. See, I'll say, I don't know, ALU signals. And I'll say logic, this will be a 2-bit ALU source EX. And then down in my control unit, I'm going to set a default value for that, which is down here. ALU source underscore EX. I'm going to default that to 0. But in the case of the add I, oh, by the way, I need to put a comment there for that. This is going to be my add instruction. And this is going to be add I and add IU, because I'm doing both here. And so ALU source B, EX, is going to be 2. Okay, is this going to be sign? What do we say? This is sign extended. Add I and add IU, both sign extended. So we're going to put 1 in there for that. Okay, end, else. And let's see, do we need if begin else, end else, if begin, end else, else begin. Okay. Or else if. Okay, next instruction. Is that all we need, by the way? Yeah, that's pretty much it, right? Put in the sign extended immediate, tell it to write the register. That's it. Okay, next one is load upper immediate. This one's pretty much the same thing. So we got to check the opcode here. 31 down to 26. equals 6 apostrophe B, and then what's the load upper immediate? Looks like 001111. Begin. Reg write EX equals 1B1, and ALU source EX is going to be, in this case it doesn't matter because I'm going to take the immediate, I'm going to shift it 16 bits to the left. So it doesn't matter if I zero extend or sign extend because I'm going to throw all those bits away anyway. So I'm just going to set the ALU source here to be 1. As long as it's anything but 0, it'll work. And remember, when you shift the B input on the ALU. So the ALU source is controlling the B input, so this is important. And then my shamped, I'm going to override the shamped. I'm going to make that 16. I'm going to tell it to shift by 16, regardless of what's in the instruction field. And the op is going to be whatever the operation code for left shift is, which is, I never remember this, so I have to look in the ALU. It looks like 1010. So 1000 left shift. Okay, everyone cool with that? Look good? All right. Next, else, sorry, and else if. Next instruction is ORI. Instruction EX 31 out of 26 equals 6 apostrophe B. We look for ORI in here. That's going to be 001101. Begin. Reg write EX is going to be 1. ALU source EX. Now this one is important. ORI is 0 extended. It's because it's logical. So the ALU source here has to be 10. And then the op EX has to be an OR, and I don't remember what that is, so these splits, ALU.S, ALU.C. According to the ALU, OR is 0001. So 0001. All right. That's it. Does that look good? Okay, well, I'm actually forgetting something here because I have the ability to send the immediate into the ALU for the I-type, but I forgot that, remember with the I-type instructions, the destination register is not RD, it's RT. Right, so I got to add that RD-RT thing as well. So that one's up here on the reg file. If I look at this write address, the write address is write address WB, and that's set. It's declared there, and it's set here. So the write address WB is actually in this clocked thing, and it's always getting RD. So we need to change that. Just say if RD-RT underscore EX equals 1B1, then I'll, actually 0, sorry. If it's 0, I'll make it 15 down to 11. Otherwise, I'll make it instruction EX 20 down to 16. 20 down to 16? 20 down to 16, yep. Does that look good? Now this part is a little strange because I'm doing two things at one time. I'm doing a mux here, but I'm combining it with a register, right? So when the clock edge comes, I'm going to select between one of these two fields, and that happens in the EX. So in the EX stage, I'm going to set the RD/RT/EX in the EX stage as a function of the instruction that's being executed. That's going to set up the input to this MUX, but I won't actually take this and move it into write address until the clock edge, right? So this is equivalent to having a MUX feeding a register. You guys see that? Why? It's simply because I'm doing this stuff inside a clocked. Now I could have made an explicit MUX and an always COM and then connected that to this, but this is kind of a shorthand way of doing it. This allows me to do both in one line of code, right? And also, like, the timing is important because, again, this is going to be set. This, and this all come from the instruction being executed, which sets the write address for that instruction when it moves into the next stage. Now, by the way, too, I want to point out that that signal is probably going to end up having to be more than 1 bit. Because we're going to add other stuff eventually, but for now I'm just going to leave that 1 bit. I can always extend that later. So RD/RT/EX. What do I call that? Oh, register file signals, right? Yeah. Don't I have a? Oh yeah, here we go, right here. Reg file signals. Logic RD/RT/EX. There we go, 1 bit. And then down in my control unit, I'll set a default for that, which is RD/RT/EX. I'll set it by default to be 0. And on the I-type instructions, I'm going to have to set it to 1. So I'll have to do it here. Override it. RD/RT_EX equals 1. And then I'll do it here for the, what was this guy again? This was ORI. Yeah, the second one was ORI, and the third one was LUI, right? Oh no, the second one was LUI. Sorry, forgot to comment that. LUI, and then the third one was ORI, and I'll put the RD/RT in there as well. Okay, you guys see that? I know this is LUI because I made the shift amount 16. So, but these guys are similar, right? RD/RT is 1 here. It's not, oh, sorry, should have been 1 in there too. There we go. RD/RT is 1 here, here, and here. Op is, this is OR, that's SLL, and that's add, which I didn't specify because that's the default. ALU source is 2, 1, and 1. These guys are sign extended, this guy's 0 extended. Reg write is 1 in all of them. Okay, all right, so I got those guys. Last one to do here is BNE. So this one's going to be the harder one. I'm going to need a PC source for this one. So right here in the fetch stage, I've got a line of code that takes PC fetch as PC fetch plus 1. I just need to have an alternative to this. And again, I'm going to use the same sort of shorthand for this one. If you're not comfortable with this, you can break this out into a more explicit, MUX into a register. But I can just say if PC source EX equals, I'll make this one 2 bits. So I'll say if it's 0, then it's PC fetch plus 1. Otherwise, it's going to be instruction. It's going to be PC fetch plus instruction EX 11 down to 0, right? Because they're 12 bits, right? There you go. So PC fetch plus the instruction immediate, 12 bits of the instruction immediate. That's the branch target address. That's if PC source is anything other than that, right? So now I have to declare PC source, which I'll put under branch control, or I'll just say control. PC control. logic, this is going to be 2 bits, PC source EX. And I'm going to need a stall signal too, which will be 1 bit. But I need 2 of them. I need one for execute and one for fetch. So I'll say stall underscore fetch and stall underscore EX. And the program counter is, or sorry, the control unit is going to control stall underscore fetch, which will default to 0. And also I need to set PC source EX, which will also default to 0. Make sense? Now the fetch is going to be delayed, so I'll just put a delay in right here for that. Actually, I'll put it here. I'll do a separate always. Always underscore FF at pause edge clock, pause edge reset begin. If reset, then stall underscore EX equals 0, else stall underscore EX equals stall underscore fetch. And this should be a blocking by convention assignment, as should this one be, because this is sequential. All right, got it. So now I'm assigning stall EX is a delayed form of stall fetch. And then finally, in the control unit, I'm going to set stall fetch, but it's going to respond to stall EX. So I'm going to put a whole if statement wraps around everything here that says if not stall underscore EX, then I'm going to do all of this. Otherwise, I won't do anything because I'll be stalled. Okay, any questions? Okay, so what do I got? I got the stall, I got the branch calculation, branch offset calculation, target target calculation. I need resolution. So the branch resolution, I'll just add down here as else if instruction underscore EX 31 down to 26 equals 6 apostrophe B, and that one's going to be branch not equal, which is, looks like 000101. Begin and end, and what should reg write be? Well, branch doesn't write a register, right? So 0. How about ALU source? Well, what am I doing with ALU? That's the first question. Well, you have 2 registers. You want to see if they're equal or not, or you want to see if they're not equal, right? So 2 registers, right? Meaning that ALU source should be 0 because I want to put both registers from the register file into the ALU. So ALU source will be 0. Actually, it's 0 by default, right? Yeah, so I don't have to do it. Screw that. I don't type anymore than I need to. All right. ALU op, how about op? What should the ALU be doing? Subtracting, right? How do I subtract? I don't remember. vsplit, ALU.SV. Subtract is, where's subtract? Oh, right here, 0101. So 0101, which is a sub. RDRT, don't care, not writing a register. PC source, well that's the tricky part. PC source is going to be a 1, but only if the branch is taken. And how do I know if the branch is taken? The 0 flag on the ALU. So if 0 underscore EX, do I care if it's 0 or if it's not 0? Well, it's a branch not equal, so I want to look for 0 being false. So I'll say if not 0 EX, then I'll say PC source EX equals 2 apostrophe B1. But also, I got to do more than that. What else do I have to do? I have to set the stall, right? Because anytime I branch, I got to also stall. I got to wipe out the next instruction that's coming in. So stall fetch equals, there you go. What do you think? Yes?
How do you reset stall back to 0? Or does it just do it?
It'll automatically do it because it's going to set to 1 only under this when this instruction is being executed and the conditions are right for the branch to be taken. So it's a fairly specific set of things that has to be, this has to be true and that has to be true. Then I'll set it to 1. In the following cycle, stall EX will be true, in which case I won't do anything in here because I've got this overarching if statement that will basically won't do anything. It'll just set the default signals here.
Okay.
Right? And then in the following cycle after that, by that time I'll have the target of the branch come in and it will have its own instruction EX and it'll do the target, right? If the branch is not taken, then I'll still subtract A and B, but I'll just continue as business as usual after that.
So will stall EX get reset then so that it's not?
Yeah, stall EX will just follow whatever stall fetch is. And stall fetch is defaulting to 0. So during the cycle I stall, this if statement will prevent me from doing any of this, but I'll still set the default signal for stall fetch to 0. So that's how it'll get reset. Basically, this if statement will cripple everything here, and this guy will set stall fetch back to 0, and then stall EX will then be 0 in the next cycle. All right, good. All right, so what I want to do with this, well, first I want to try to compile it. So I know I'll have a bunch of errors here. Yep, typo, line 124. Oh, look at that, worked. That's surprising. I'll probably get a runtime error there when I simulate it. Speaking of which, let's write a program here first of all. We got to get a program to. Okay, so what I'm thinking. Oh, one other thing I forgot here. The GPIO. We need that working too. How do we get GPIO to work? That's actually pretty trivial. I'll do the output for you. I'll give you guys the output. You guys will have to figure out the input on your own. So I'm going to add a signal called logic GPIO out enable. And then I'll have this thing that says always underscore FF at pause edge clock, pause edge reset, begin. If reset, then GPIO out is going to be 32 zeros. Else, if GPIO out enable, then I'll set GPIO out to be what? What does it get? Read data 2, according to this. Read data 2 EX, right?
Is that an LMS too, 32 bits?
Oh, sorry. Yeah, sorry. Yes, thank you. Should be 1. No, sorry, 0. Yeah, there you go. And read data 2, that's a thing, right? Yeah, it's a thing. Comes out of here. Right there. Okay. That's it, right? Oh, yeah, and then my control unit has to deal with that too. So control unit has a default for that. GPIO underscore out underscore enable is 0 by default. And if what do I have to do for that? You guys remember? It's a shift or something, right? Else if it's the criteria there is instruction EX 31 down to 26 has to be zeros, right? And instruction 5 down to 0 has to be the shift, what is it? Shift right logical? I don't remember. What do we say? Shift right logical, yeah. So GPIO out's going to get regs RT, which is read data 2, because our RT is the second read data. Shift right logical, and then if I look at my sheet here, shift right logical is got a function code of 4 zeros and a 1 0. Right? 1, 2, 3, 4, 1, 0. And what else? There's another criteria, right? Oh, that should be EX, by the way. The third criteria for this to work is the shift amount has to be 0, right? Right?
Yes.
So 10 down to 6 is got to be 5 bits of 0. And actually, we should have went a step further with this because that RD should have been 0 too. Or it should have equaled whatever RT was. So we don't have a side effect of blowing away RD. But we didn't think of that. Charles didn't think of that. So I am just going to put a 0 when I do this in my code to prevent that nasty side effect. But according to the control unit, it's just pretty much anytime you do a shift right logical by 0 bits, it'll do the whole GPIO thing. So GPIO underscore out underscore enable is going to be set to 1. End. All right, that's it. Good. Got it. Hopefully that works. I'm surprised I didn't screw up any of these begins and ends. I usually do that. Oh, I did. 55. 55. Oh, that's way up here. Oh, that was, oh, yeah, that's easy. Okay, I got that. That's end for that. Okay, cool. All right. Still 55. What I screw up here? If reset, then GPIO out equals that. Oh, else if that, then that. Yeah, what's?
It's a semicolon and if.
Oh, right here. Yeah, thank you. Semicolon. Okay, got it. All right, cool. Got it. All right, so what's the program we want to write for this? I'd like to write something that just does a counting sequence that counts on the hex displays, right? So actually, I'm just going to use the one I already wrote because I'm running out of time here. I wrote one at some point. Lecture stuff 2. Old? Yeah, old. Counter.s. Counter, I think. Okay, let's look at that. Open counter.s. Okay, so here's my program. I'm going to initialize register 2 with 0, and I'm going to have this other register that I'm going to set to 10 million. 10 million, I'm going to use that to slow things down on the board. So I don't want this to count 50 million times a second. I want to be able to watch it count slowly. Then I have this other thing called count limit is going to be 16. So this will be a nested loop where I'm going to do a shift right logical which is going to take the value at register 2. That's my count. And it's going to output it to the GPIO. So that'll spit it out to the GPIO. Then I'm going to have a nested loop, and inside a nested loop that'll iterate needlessly for 10 million iterations, just to slow things down, right? So I'll initialize register 4 to 0. I'll add 1 to register 4. And as long as register 4 doesn't equal register 3, I'm going to branch the delay. So I'm going to keep doing this until register 4 catches up to 3, and 3 is 10 million. And then I'm going to add 1 to 2, and I'm going to go back to, as long as register 2, which is my count, doesn't equal register 5, which is 16, I'm going to loop. So this should count from 0 to 16. It should be real slow so I can watch it happen, and it should print to the hex displays there. Make sense? Okay. So I need to, sorry, I guess I assemble this, and then do dump memory, and then do hex. I don't think it, yeah, hex dump the file. Call it, I'll call it counter.dat, I guess. And then back to here, if I need to use that, I'm going to change that here to counter.dat up here so it'll load the right program. Okay, and then I need to simulate this first. I could put this on the board. If I do that, I have to have a wrapper too that connects, that has the 7-segment decoders. But I'm going to test this first because you never want to go straight to the board because chances are it's not going to work. You want to simulate first. But the problem is, in order to simulate, I can't simulate it if it's going to be simulating, if it's going to be counting to 10 million, right? So I'm going to have to reduce that too for the purpose of the simulation. So I'm going to bring this down to 4 just so I can realistically simulate this. So I'm going to save it. I'm going to re-export it. I'm going to say, sorry, I have to assemble, sorry. Then dump memory, hex, dump to file, counter.dat. I got to put it in the right directory. Lecture stuff. I don't think that worked. Lecture stuff. I used a backslash. Counter.dat. Okay. Yep. Okay. All right. So time to run it. Come back over here. Let's do vlog star.sv. vsim no vopt CPU. Come on, model sim. There it is. No runtime errors? Come on, no whammies. Good. All right, so I'm going to say add. I don't know if I showed you guys this last time, but if you say add to log all items in design, it'll log everything, and then I'll also just add wave to everything that's in the CPU. And the one exception to logging is the memories. So I want to be able to see what's in my register file, so I'm going to have to plot that one separately because the log won't log it. It doesn't log memories by default, even if you tell it to log everything. So I'll add that to the wave. Okay, and then hit the little mountain button. Here's all my signals. And then I need a do file to run this because I don't have a test bench yet. So I'm going to bring in my do file from, I'm going to bring in my old do file, test.do, and show you how that works. Very simple. It just does a restart -f. It sets up a clock. It forces the reset. It runs 100. It forces the reset back down and runs 500. So if I go to model sim, I can say do test, whoops, sorry, command line window, do test.do. What the heck? Is this the lab? All right. All right. Okay. Well, something happened here. So I'm not getting any instructions out. So that's the first. So the first thing you want to check whenever you run one of these, you look at the basic stuff first. Do I have a program counter? Yeah, program counter is alive. 0, 1, 2, 3. So the program counter is ticking up, but I don't have the instructions start out at 0, which makes sense because the reset set up the first instruction to be 0. But after that, I got nothing. So to figure that out, you got to go and look at I'll have to look at the instruction memory first of all. Well, let's look at PC source since I've already got it here, because that would be an issue. PC source is 0, so yeah, so that should. I'll double check the code, just a quick sanity check here. So the PC source is PC fetch. Oh, that's actually just the PC fetch, right? I'm sorry. Yeah. So I mean, there's nothing that could be going wrong here unless my instruction memory wasn't being loaded, and probably there was a warning about that I missed. Maybe no. Oh, illegal character dot on line 1 of counter dot dat. There you go. That's the problem. I see. Got to make sure you check those warnings. So I will try to fix this within 1 minute. Counter.dat. Oh, yeah. The counter.dat is the assembly instead of the hex dump. I don't know how that happened. So I will once again go to dump memory, text, hexadecimal. Maybe I I might have accidentally said text something here, text data segment window, I don't know. Dump the file, counter.dat, yes overwrite, and then I will valid, there we go, that looks better. All right, now because I changed only that, all I got to do is restart. I didn't change in the Verilog, so I just have to rerun the simulation. All right, there we go. So there's the instructions coming out. Now, how do I know if this is working? I have to look at my registers for now. And so it's not scrolling, but I had my registers down here. So I hit the plus, the little plus sign here, and you can see how the registers change and what oh, it worked. Okay, cool. So what's supposed to happen here, if everything is working, is looks like it's working. Check that out. So let me run it a little bit longer. Oh. Well, register 4 is ticking away. Look at that. 2, 3. That was my delay register, my delay counter, right? Then I had that was the inner loop. Then I had an outer loop that was counting up register 2. So now we got to see if register 2 is incrementing. Oh, look at that. Oh, looks like something's wrong. No, it's working. Yeah, there it is. Register 3 has to count up to 4 before we increment register 2. The other cool thing you can do is if I zoom all the way out, I can look at my stalls. So if you look at like the stall signal, well, there's a GPIO, right, by the way. There's my GPIO writes right there. That's when it's updating the hex displays. I've got my stalls. There's the stalls. That tracks all the branches. So if I took this, damn, I almost made it. I could put this on the board right now, and I'd have to compile it. It'd take a little longer to compile it. But if I put this on the board and I readjusted that counter to 10 million, it would tick up about once a second or so. It would just add one. Of course, that I also have to bring my hex decoders in and stuff too. But that would just look like. Lecture stuff. Old. So that would look like this. So I have a top level design that just has I used the for loop here to generate the hex decoders instead of copying and pasting 8 of them. But yeah, that's the top level design with that design and that program, and it would make the board turn into like a little stopwatch counter thing. So I'll put this on the website. This should give you all nice template to work with. You don't have to use it, obviously. My code is very compressed and dense. Obviously, I'm putting everything into one giant file, which is kind of ugly. But you could feel free to use my stuff, and I'll put this online. Okay, great. Then I'll see you next week for the exam. If you have any questions about the practice questions, let me know. I've got the questions and the answers on there. I've only got about 9. Oh, yeah, thank you. I've only got about 9 questions, so you can expect to see just about, almost, yeah, pretty much all 9 in some form.